Hello everyone. Today I, Shan Sheth, with Siddharth Agrawal, Arya Shah, and Shreya Sheth will be showing our report on sequential data predictions. As we all know, over the years, machine learning has advanced and it's used all over the world in various technologies. One of the most important applications of machine learning is natural language processing and time series forecasting. It is based on various machine learning techniques like hidden Markov models, artificial neural networks, recurrent neural networks, long short-term memory, etc., which we have discussed in our paper by using application in POS tagging and stock price prediction.
Markov models are stochastic processes where the next state, or j, is dependent upon the current state of the process, or I.
They can be further denoted by a probability matrix P of ij, where I is the current state and j the next.
Now, hidden Markov models are an aspect of Markov models where there are quite a number of unobserved states, but in the end, the output of the probability matrix will still be independent of the unobserved states. Markov models have quite a number of applications in various fields such as computational biology, stock prediction models, etc.
So part of speech tagging or POS tagging is a natural language text processing technique that is used to understand the meaning of a given text or a corpus, which is data. What essentially part of speech tagging does is these n words will be broken down and assigned like a verb or an adjective or a pronoun, and all these tags are later used to basically predict and complete the input. This is completely done using hidden Markov models. And basically what hidden Markov model does is it uses transition probability matrix and the emission probability matrix. So in A, which is the transition probability matrix, we have like given a tag, how often is it associated with another tag? And the emission probability will predict that given a tag, how often will it be associated with a word. So given these two metrics, when we use these two to build a hidden Markov model, we will be able to correctly identify and complete a given input. We also use a Viterbi algorithm here, which is essentially a decoding algorithm. This efficiently predicts that given out of n number of outputs, what would be the most reliable and the best output.
We also use hidden Markov models to predict stocks by classifying stock trends as either going up, down, or staying stagnant. Then we are able to make a transition probability matrix that maps the current stock price to the probability of stock prices tomorrow. Here we can see the transition probability matrix as well as the steady state vector. The steady state vector is the probabilities that the model converges to over a long period of time. Artificial neural networks are models which use repeated matrix dot product and nonlinear activation functions which are applied element-wise to get their predictions. If the nonlinear activation function was not applied, it would be equivalent to a single linear transformation, which is not very useful to predict complex data. Nonlinear activation functions are applied after each matrix dot product and addition, so that each layer can progressively learn more about the dataset. The error or the loss is calculated by subtracting the actual data with the predictions and squaring it, and the derivative of this error with respect to weights is calculated, and we are moved in the opposite direction of this derivative or gradient. This allows us to iteratively get better weights in our matrix, and we are able to optimize the model to the minimum error state. RNNs are sequential neural network that can incorporate both past data and current time step data to predict the future stocks. However, they suffer from a vanishing gradient problem, as you can see here. By the time they reach the 7th time step, they would have already forgotten what happened on the first time step. LSTM remedies this by adding a forget and input gates that learn what information to forget and what information to add to the memory state. The output gate then uses this filter set of information to predict the future. This allows the model to use both long-term and short-term trends to predict the future and allows the model to have a longer memory retention. We go from hidden Markov models, which are memoryless and can only take into account one factor. Then we go to artificial neural networks, which can take into account multiple factors but are still memoryless. Then we go to recurrent neural networks, which do have memory, but it's very short-term. And then we go to LSTMs, which have long-term memory, and they're able to use long-term and short-term trends to predict the future. This is why we see the models progressively become better at predicting the stock market. We also innovated on previous strategies by introducing a custom loss function. Typically, a mean squared error is reduced, but by changing the model to predict how much to buy and sell each day, and then returning the loss function as negative of the profits, we can optimize this loss function and thus maximize the profits for any given trading period. In conclusion, LSTM were the best at stock price prediction and yielded the lowest mean squared error when compared to safer investments like fixed deposit, government bonds, and mutual funds, which usually have 6 to 12% mean return on investment per year. This model was not all that much more effective at only 11%. If you had multiple LSTM models for each of NSE India stock market, we could increase the profits as we could exploit opportunities of earning money more often.